I'm always excited about these talks because it's great to share with the public. And yeah, I've got a lot going on right now. We are working in the laboratory on certain technologies that are very exciting. And as well, of course, I'm working on this paper that unified physics, that does the final job on unifying physics using utilizing the holographic mass solution. And every time I turn the corner on this thing, it amazes me. This fundamental ratio that I identified in the holographic mass and quantum gravity and holographic mass paper in 2012. And actually, I identified it in 2011, but you know, it took a while to publish. And it really is a fundamental invariant relationship in the universe. That is, the universe doesn't really do mathematics, of course. It does, you know, ratios, relationships. You know, relationship of forces, relationships of size, density, you know, and a relationship of wave forms, phase relationships, you know, phase angle, and so on. And so what's happening with this paper is that as we're writing this, as we discovered this unifying ratio, this unifying relationship of volume to surface ratio, from the Planck scale or even the sub-Planckian scale to the universal scale, is that these relationships become more and more obvious in terms of, for instance, the relationship of the four fundamental forces and how they interact at each scales, and the relationship of densities, the relationship of electromagnetic fields, and all this. And all this, these relationships, when you examine them at different scales, all of a sudden output the forces, it outputs the fundamental constants we see, like alpha, for instance, or the Reinberg constant, or the G factor, and of course, the gravitational constant. So for the first time, for instance, in history, we're able to from a theoretical base, account for the gravitational constant with some 10-digit accuracy, which is remarkable because G, or the gravitational constant, in our equations is very problematic because it's only known with some accuracy, and even that's debated, with 5-digit accuracy from experiment. So
But the precision's too small for the precision level that you're working with.
Exactly. And it's a problem because in the holographic mass solution, G is involved in all the Planck units. G is involved. So it drops the resolution, right? It drops the accuracy to 5-digit digit accuracy on all the equations that G is involved in. So since, you know, in quantum theory, we have measurements that are known with 13-digit accuracy, like the G factor, or you know, the Reinberg constant with 12-digit or 11-digit accuracy, and so on, which is a level of accuracy we deal with in the quantum world when you try to incorporate, you know, when you're describing the quantum world with, you know, this fundamental pixelation of space-time, which utilizes the Planck units, you are limited to a 5-digit accuracy, right? To 5 significant numbers accuracy because of G. And it was definitely good enough to predict the radius of the proton, which was actually, you know, much worse. It had 4% inaccuracy when I predicted the radius. I found out that actually the standard model radius was 4% off, and that was the prediction I did in 2012. That got confirmed, and now it's been rectified, and the co-data value is the prediction I did. Um, but more importantly, when we applied the equation at the deep level of particle physics in quantum theory, and to the fundamental constants, like the Reinberg constant, like alpha, and so on, we were limited. We had this problem that G was limiting us because we were using Planck oscillators, what I called the spherical Planck unit, right? So we were using PSUs, and um, and that's what's amazing in this paper is that but even with that, we were able to figure out this ratio, volume to surface ratio, and apply it to all the scales. And as we applied it in all the scales, and as we, manipulated the various equations to output, and it was outputting, certain constants, we were able to back engineer from the data it was giving us what G should be. And so we were able to back engineer G out of these fundamental ratios and get G with, 11 to 12 number accuracy. And we know it's accurate because when we apply that G, right, to, of course, the first 5 are the same than the measurements, but we have all these other numbers. So how do you verify that these other numbers are right? Well, you take that G and you put it in the equations, and then you output constants that we measure very precisely, and it outputs all the right numbers, right? Not just for one constant, not just for one particle, but for all of them, right? For particle mass, radiuses, for instance, the electron is well known, and so on. And it outputs all the right things, the Reinberg constants, all the G factor. And so we know our G now is absolutely accurate, right? And that's really, that right there is remarkable. But the fact that now you take all these constants and you take all these equations and you have 12 to 14, in some cases we have 14 digit accuracy, in some cases we're exact, meaning we don't know how far the accuracy is, but because of the relationship we know we're exact. We have this template, right, from which you can, so now you go from the Planck scale, right, with now the Planck scale is known to 10 to 12 digit accuracy with the new G, and now you go from the Planck scale all the way back up to the universe, and now you have huge accuracy on cosmological things, like the background temperature of the universe, the acceleration, the size of the universe. All of a sudden everything is upgraded, where usually in astrophysics, right, or in astronomy, but in astrophysics, I mean, basically, if you're in the same order of magnitude, you call it good, right? Right? I mean, if you're within 1 0 at one order of magnitude, which is huge, an order of magnitude can half the size of the universe, right? So, but it's that type of thing that that all of a sudden just goes away, because because you have this level of accuracy at the quantum scale, right? Now, and those equations all of a sudden are able to give you information about the universe, right? Because now it's unified, so it's all the same equations. Now, when you apply it to the universe, now you have that level of accuracy for universal events. So that is um, that is like remarkable. It's unbelievable. Never mind that we, as a result, although we unified everything, now we have things that are like more decorrelated, meaning that um, it used to be that in order to know the radius of something, you needed to know the mass, right? In order to know the mass of something, you needed to know the radius. But with these equations, now you can just output it directly because the relationships are known. So for instance, you can look at the proton and output the mass of the universe, or output the radius of the universe. As long as you have one part of the scale, you have all the other scales. And the radius and the mass can be independently found without knowing anything about that scale. So you can look at the proton and go, oh, okay, the radius of the universe is that much, and the mass of the universe is that much. And so although you know nothing about the universe, with these equations, you just apply it to the proton and you know the rest. You can figure out the electron, you can figure out galaxies size, average size of galaxies, you can figure out, average size of stars, things like that. And so it really is a whole new way of thinking about physics, where it's unified, but literally unified, meaning like from any scales, you can figure out any other scales because the relationship are invariant. They're always the same. And so it's really amazing.
So almost anything we know, it's always a relationship. We know one thing, how it relates to another. And that's almost like a definition for information itself. What's the relationship?
Mm-hmm.
And so it's really remarkable that phi relationship, that relationship you discovered in the quantum gravity and holographic mass solution,
mm-hmm.
that ratio is almost the key to understanding these relationships across the scales, from the Planck scale to the cosmological scale.
Exactly. And initially we weren't sure how to do it. And with more and more we write these equations, and more, it just always come back to that fundamental phi. And I want to clarify, this is not the golden mean phi. This is the phi I identified in the, phi in physics is commonly used to describe a ratio, a relationship. And that's why it's used for the golden mean, which is a ratio, right? Like the Fibonacci series. And so, but in physics, it can be used for any ratio you're trying to identify or you're identifying. So I used phi in my paper. So that's the letter we use to describe it. But yes, it's a surface to volume ratio that describe the information transfer, as you were saying, that's occurring between the inside of a system and the outside of a system. And all these things I'm talking about might sound, like, somebody's writing Russian dolls. Like Russian dolls. And the relationship of the smaller doll inside the bigger one, except they're Russian spheres, right? So I don't know, they're not Russian, they're universal spheres. But you could think of it as this thing that's like moving like from one scale to the other, right? But that maintains a relationship so that you can think of it this way, so that if I made the pixel size, right? If you went from, the let's say you went from um, one scale to another, right? You and the first scale that you're doing with the lower scale. So the Planck to the proton to the electron, right? Then you would do so for, let's say, you for the proton you're using the Planck as a spherical Planck unit, like as a PSU for your pixel size to get the ratio, right? Then if you went from the proton to the electron, you could use the proton as your pixel size to get the electron, and so on. You could scale like that, and the ratio would always be the same, basically.
But your level of precision is at the Planck level of precision.
That's right, exactly.
Amazing.
which
Wow.
which now we have to very high degree because of this new G. It's fairly complex because there's so much in physics, right? You have all these constants, you have all these particles, you have larger scale universe, all this stuff. But it comes together in such a way that is so beautiful and so precise that, you know, it's, you can't, what's crazy about it is that more you write the math and more you write the physics, more you see the pattern, and more you see the pattern, more you see that you can't move anything in the framework, meaning everything becomes super defined, right? So that you realize, like, you know, on the 11th number after the period, right, on this constant, if you budge this number by 1, right, like instead of a 5 it becomes a 6, for instance, right, then everything else in the whole thing like goes wrong. So you don't have margins, like everything becomes like rock solid, right? Like it's defined to like the nth degree precision, right? It's tuned very, very precisely to produce our world. And you can see that like it cannot be like, it's because now you see the relationship, now you see, you know, that it's one thing, right? It's not like you have 4 forces. It's not like you have, you know, 20 different constants. All these things are unrelated, which is currently the case in physics. Like many of the things are not related. Some of them are, but you know, we don't see a relationship in standard physics between, for instance, the weak force, right, and the strong force, or the weak force and the gravitational force. You know, we don't see her, but in these equations, you see those relationships. You see how they depend on each other. You see that and you see that the precision of them, right, that, you know, defines, you know, how everything is working. And so then you see the oneness of the thing, and it just blows your mind. It just blows your mind.
Well, it just seems to me like that's been the goal for unified physics, going back to Einstein. Even Paul Dirac, was, that, you know, amazing physicist, was working on that one ratio that would tie it all together.
Right.
It seems like
Paul Dirac actually identified that ratio, and he was very, very close. He had it loosely because he didn't have a fundamental mechanics. You know, he didn't have a mechanism to describe where that ratio was. He just noticed it in physics. He noticed that there was a ratio of approximately 10 to the 20th that just kept on flying around everywhere, like the relationship between the strong force and gravity, the relationship between the radius of the proton and the radius of the universe, the relation, like he noticed like this 10 to the 20 was floating around, and he said, this has got to be something, like this is, This can't just be a coincidence, right? It just keeps popping up everywhere. And he called it the large number hypothesis. And it was at the end of his life that he started to talk about it publicly. It was hard at the time, and it's getting easier, but still hard for physicists to think that somehow the proton is related to the universe. You know, somehow the size of the proton is related to the size of the universe. It's hard for them to think that way, although if you think about it for a minute, the two are in, like the proton is inside the universe and it's oscillating and the universe is oscillating. So it's not so far-fetched to think that there's some kind of harmonic relationship between these scales. I know they're hugely apart, but the universe is full of protons and they're all oscillating and they all emerge from a timeline that goes to singularity, that goes to zero when they were all unified, right? So it's like clearly there's a relationship. It's not far-fetched to think of it as a relationship, and now we're seeing it, which is remarkable. You know, it's and I'm so proud of Dirac for having, you know, there's interviews you can find on the internet of Paul Dirac talking about the large number hypothesis. And in his case, you know, he thought it had to do with the variance of G, actually. He thought that it had to do with the variance of the relationship of gravity in the universe. And what we show is that that was really close, but the variance is in the density of the vacuum. The variance is in the density of the fluctuation in space, which produced G. So it's actually, he was very, very, very close. He was just missing the mechanism.
Yeah. Where's the variance?
Meaning that when the universe grew, the vacuum density dropped, right? But you know, so the relationships were generated by this change, right? So and this is what the equation shows, right? That's why we end up with dark energy at the cosmological level, where the vacuum density is like 10 to the minus 30 per centimeter cube, right? 10 to minus 30 grams per centimeter cube. And at the quantum level, it's 10 to the 94 grams per centimeter cube. There's a 120 orders of magnitude difference in density. That is because of this. So Dirac was really, really close. But because he didn't have the mechanism, he assumed a variance in G, where in fact is a variance in the vacuum structure. Now we can really unify physics and really help humanity go to the next level, you know, because when you start to see the physics of the world this way, you really kind of get a sense that the universe is you, meaning you feel this relationship very profoundly. You know, you don't just, all of a sudden you're not just in the universe, you're part of the mechanics of the universe, right? And so now you start to realize, and you just apply the equation to yourself, you know, and you start to realize your biology, your physics, and all this is just an information exchange with the field. And that exchange is actually what transforms our reality, meaning our reality is part of this constant information network that's learning about itself, and you're part of this. So all of a sudden you feel less isolated and part of a larger, you know, and you see it in the equation. So it gets out of like being a dogma, and it becomes a reality. And this is why, you know, it's so important for people to take that course we have on our website, because, you know, reading that course, and we're gonna add a module that will address this new paper as soon as we have it out. And it will be great because we can literally just go through all of the equations and explain what they mean. And that becomes like, you can like integrate that in your experience as you read it. So I'm pretty excited. We got 47,000 people taking the course right now. 47,000 people, and we need to get to 100. We got to get to 100 by September. Let's do it, folks. Let's get people registered. Let's take the course. It's free, it's easy, everybody can do it. I had my kids do it, you know, and then the discussion gets stronger and stronger, and we can talk about it, and we can transform all together.
Definitely. You can find the delegate course at the Resonant Science Foundation website. It's free to enroll. Definitely go and check it out.
Yeah. In general, people really appreciate it. And you can meet people from all around the world, you know, that are taking the course. You know, we have a forum there. You can participate and ask questions. And, you know, we have the research team answering, and we have these 2-hour meetings every month. And it's a lot of fun, and we learn together and transform together, and we're going to continue to update. So that's an update that's going to come soon. We will get a 7th module to our course, which is going to be awesome.